Okay, any questions so far? Anyone? Let me see. There's a question been raised which I did not see earlier. I do apologize. Not zero anymore, Montoya. You're right. Okay. So the next one, we're gonna look at an example. Yeah, we're gonna look at this example over here. Copy. And then I'm going to copy the cross section. Okay. So this is example number 2. So enough of the theory, okay? Okay, example number 2. So this is our structure. Okay, so knowing that the clamshell has been tightened on wood planks being glued together until P is equal to 400 Newton. Determine the section AA. So that's a section AA, the stress at point A, the stress at point D, and the location of the neutral axis. Okay, the location of the neutral axis. Right. So for this case, okay, we see how the structure will deform. So we can sketch, okay, sketch how the structure will deform. So the structure, we just need to do half of the structure, okay? Okay, so at this point, I'm going to call this point C. Okay. Failure will occur at point C. Yes or no? Somewhere at point C. It's going to somewhere at the center. Okay. So when that's the case, the next thing we're going to draw, let's sketch how will this structure deform. Okay. So I'm going to sketch how will this structure deform. So when this is deformed, it will look like this. Why it will look like this? Right? Because P is acting in that direction. It's going to force it open. Right? So this is P. So when that's the case, right, we know that the moment will be acting in this direction. Right? You're bending it. So this is your moment in your Z direction. Okay. So why I call it Z direction? So now I draw the transformation, right? So this is point X or X axis, Y axis. Okay. So this is our rotation at Z. The curvature of rotation of Z and the moment of the curvature, this curvature, is the same, right? The curvature is going in that different direction, but the curve is in that orientation. So that's why moment in the Z direction. So from here, directly based on the analysis, you know that this is going to be under compression due to moment, and this is going to be what? In what? Tensile. Okay. So with this example, what we see on the diagram on the right, that is our cross-sectional area. Okay. So when you have a cross-sectional area, immediately draw this out. Immediately draw this out. So we know that based on cross-sectional area, right? We know that over here, this is our Y, and this is our Z. Yes or no? And then this is our rotation in the X direction. Okay. So from here, because we know that the moment is in the Z direction, so the formula that we're going to use is stress in the X direction is equal to Px divided by A, right? Plus, don't worry about minus first, okay? Don't worry about plus, minus if you're not sure. Oh, shoot. Okay, it's the analysis later that we carry out whether is it plus or minus. So if now it's just a general equation, put all plus. I'm fine with that. Okay. So we know that this is mz over izz multiplied by y. Okay. So we know that we're going to find izz. Right. So we are aware that we're going to find izz. So we know that this direction is our izz. Exactly where the centroid is. So this is our centroid. Where is it? We don't know yet. We need to find it. Okay. So centroid. So, but why am I doing this? Because anything that below the centroid is going to be compression. Anything from the top is going to be what? Tensile. Okay. So this is the most important thing. Okay. Right. So from here we know that Px is equal to 400. Right. Px equal to 400. Moment about Z. Now, moment about Z, you have to be really careful. This is my advice. Okay, this is my advice. Okay, my advice is to this. For this case, take moment. Okay, take the datum from the top. Right, take the moment from. So take datum from the top. So some of you might ask, yeah, I'm also stubborn. Okay, so why? So actually, the symbol for datum is not okay. That's right. So take the datum from the top. Okay. So why take the datum from the top? Is this? So when you find your centroid will be from the top to here, right? E. Right. So at this point, where the datum is the datum is at this point over here. That's your datum. Okay, that's your datum. You take it from the top. So when you calculate your moment of about Z, all you need to do is Px multiply by 0.05. Okay, 0.05 plus by E. Okay. So this is datum from the top. Right. So you can see how I pick the datum is I'll pick on the same side as where the P is loaded. So you take the 50 and then you plus the E. So what if now you want to become different? I'm not saying different is no good. It's good to become different. Okay, but when you are different, you for this case, okay, I'm very specific for this case. Okay, I'm a person that is I'm always pro to do something different. Okay, but for this case, if you do something different, now let's say we do, so this is our datum. Right? That's our datum. Okay, so you decide to pick your datum over here. Okay, so you find this is your what? This is your E at I call it E bottom. Label this properly, Eugene. Come on. So this is what I call E bottom. Okay. So when you do that, you have to be really careful when you calculate your moment. Okay. So MZ now is equal to PX, right? You have to add your 0.05, right? And then you have to add the 0.02, right? 0.02. And now you have to minus your E bottom. Okay, you see where it's confusing. If you forget to minus if you forget to do this, right, you are a big doodah, you know, you're in trouble. So this is taking the datum from the bottom, right? And we know E is also equal to 0.02 minus by E bottom. Yes or no? It's the same location. So you can see why. If you this is only 2 terms, yes or no? The if you take from top, if you take from the bottom, it's 3 terms, and if you forget to minus, that's it. Okay, and when that's the case, what will happen is you get -1 mark, and provided the rest of your analysis is correct. So why make things difficult for yourself by doing E bottom? Okay, so this is what I want to emphasize for all of you. Okay, so the trick is what? If this is the force, okay, this is the 50, right? Where it touches your structure, that's where you take your what? You take your datum. Okay, this is where you take your datum. Okay, don't take your datum down here, because the 50 is not touching the datum down here, is it? Okay, I hope you understand what I mean. If not, maybe you can watch the video further, or repeat it. Okay, so that's why I always take datum based on the location of the force. Okay, I'll write down here. So the datum, the preferred datum location should be on the same site as the centroid. Okay.
Sir, I have a question.
Yep.
So in that first moment, mz equals px times 0.05 plus e. So where are we taking that moment in the
At the top.
diagram?
At the top. So the moment is based on this P, is from the top, right?
So we're looking at the xy plane now, right?
We are looking at the XY plane. Yes.
Okay, I'm like not able to relate how that e is coming into play. So
So the E, if I look from XY plane, E is here.
okay.
Okay. So this is a centroid. Does that make sense?
Mm,
So on the right hand side is your cross-sectional view. You slice it, okay, and you view it. So if I look at scale, this is this distance, for example, this distance is 10 millimeters, for example. Okay. Over here, the scale, this distance is 10 millimeters. You get what I mean? It's amplified. Hello?
yep.
You get what I mean? Yes or no? So if I were to draw this to scale, the cross section looks like this.
Okay.
Does that make sense now?
Yeah.
I know it's a bit confusing. This is how the question is phrased. Okay?
Yep.
Yeah. All right. Okay. So the preferred datum is the same site as the applied force. Okay. Same site as the centroid. So the preferred datum location should be on the same site as the centroid. The preferred as same site. Wait, the preferred, I lost where. So the preferred datum should be located on the same site as the applied force relative to the centroid. Okay. So now I'm going to take this image over here. Okay, so we are going to, okay. So like I mentioned before, so now at this view, this is your Y, Z, okay, rotation about X, okay. So I'm not going to do this again, because I think now you guys of you are capable of finding centroid. Okay. So on top is the again, and on top is the datum. So while doing so, we have calculated. Okay, I'm not going to show you down here the the formula is always the same. Okay, so the calculated, so the centroid, the y bar is equal to 8.154 millimeters